Hey, everybody. So today is section 3.4, transformation of functions. I'm going to follow the PowerPoint quite a bit, but I might veer off of it a little bit. I think that this section might be better done a little bit differently than the PowerPoint's doing it. So I'll do a combination of both. So let's see what we're going to do. So transformation of functions, basically, we're going to look at vertical and horizontal shifts. Well, let me just put this all into one real sentence. We're going to look at just basic graphs, the ones that we talked about in 3.3, I believe, where we looked at just the different shapes. And what we're going to do is figure out how they move given the equation. So they'll either move vertically or horizontally, and they can flip over the x-axis, they can flip over the y-axis. And so I'll go through all of that with you. Yeah, well, we're not going to do. Yeah, so we won't be doing transformations of piecewise functions. I will probably do the combination of transformations. I don't believe there's any on your homework, but I'll still do it. All right, so let me see. I think that I'm gonna just get a slide of my own and start this without their slides. So give me 1 second here. Okay, so basically we have these things we call transformation of functions, or sometimes people call them translation of functions. And we have both vertical, like things can go up or down, or horizontal, back and forth, right? Or a combination of both. So let's start off. Vertical is a little easier than horizontal, definitely. What I think I'll do is I'll do the vertical. And well, let's see how it goes. So let's do vertical. Okay, so the first thing we're going to do is stretching and compressing graphs vertically. So what that means is, let's say I have a, well, let me first write down what it looks like. So if I have a function, let's just call it f of x. And let's say f of x is equal to the square root of x, okay? Then a vertical stretch or compress will basically look like this function, but it will have some kind of constant in front of it. Okay, so for example, if I were to say I have a constant a, we'll call it a, so then it's just like multiplying whatever the y value is by a. So if I multiply both sides of that by a, I would get a times the square root of x, right? So now, if I want to stretch it, which means basically I'm taking it vertically and I'm pulling like the top of it up, so it's getting taller, then that's called a stretch. So a stretch is when A is greater than 1, okay? So when A is greater than 1, we're going to stretch this graph. So let's look at it both ways. And I'll try really hard to make a nice graph because it is a little bit important. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see that I don't really care about anything negative because the square root of x, just the square root of x is never negative, right? So when x is 1, y is 1. And there's a bunch of numbers in between, but I'm just going to pick the whole numbers. So when x is 4, y is 2. And when x is 9, y is 3. So if we were to graph this, and obviously when it's 0, it's 0. So I'm graphing these points for the square root, and hopefully you know that this is what the square root function looks like, and it just kind of keeps going on, right, forever. And that is just, this right here would be just the square root of x. So if I picked a value where a is greater than 1, then let's pick a equals 2. So now I want to graph f of x, or I'll call it g of x so we don't get it confused. I'll graph g of x is equal to 2 times the square root of x. So now when I graph this, every value of x is going to stay the same, right? So when x is 1, the square root of x is still 1, but now notice I'm multiplying by 2. So it's going to go up to 2. And then still the square root of 4 is 2, but now it's times 2. So that's going to 4. And again, the point I have at 9 was 3, but we're multiplying it by 2. So now it's going to 6, which I didn't draw in. So let's say 6 is right here. So let's say this is my graph of 2 times the square root of x, right? And hopefully that makes sense, because what I've done is every time I evaluate the square root of x, now I'm multiplying by 2. So y is doubling, right? So that's why it looks like it's stretching vertically. And then if a is basically between 0 and 1, we're not talking about negative values. And if it's 1, it's just the regular 1, right? We're not changing it. But if a is between 0 and 1, it's a fraction, and we'll call that 8. So we'll call this is g of x, and we'll call h of x equal to, let's just call it 1/2 times the square root of x. So this is a compression, because what I'm doing is basically, think of it like I'm pushing it down, right? So now when x is 1, when I plug in 1, I get 1. Square root of that is 1/2. So it's going to be, oh, I don't want the color. It'll be right here. And then the square root of 4 is 2, but now 1/2 of that is 1. So it's going to be right here. And then we have the square root of x, which is 3, and we have 1/2 of that. So we have 3/2. So that's about right here. And we can see now, hopefully, it's not very great. Probably the best thing to do would be to maybe redraw this one a little bit, because it should be pretty much right in the middle of those other two. So let's just say it goes like this. So we'll make this the square root of x. This is 1/2 times the square root of x. And the other one is 2 times the square root of x. And you can see that depending on whether you have a fraction or you have a whole number that you're multiplying by, or even anything greater than 1, it's either going to stretch up or compress down. And that's how vertical works. And you can see that this is an important point. To tell the difference between horizontal and vertical, notice this is outside of the function, okay? So when we get to the horizontal, you'll see, if I did horizontal, let me just write it over here so you can see the difference. So I won't graph it here, but I'll just say, if it was a horizontal, stretch, compress, the function would look more like f of a times x. So it would be like the square root of ax. So now the a is under the square root because it's inside the function. So one way that may help is if you see it like this, notice this is directly affecting x because it's inside the function, right? But the one vertical is outside the function. So it's actually not affecting x, it's only affecting y. Okay, hopefully that's clear. I'll go through the slides after more quickly, but I think it's better if I explain them one by one without all their words, because this is mostly a picture thing. Okay, so then also vertically, we could have a shift. So if I'm shifting vertically, then I'm shifting up or down, right? So we can use the same square root. So we'll say f of x is equal to the square root of x. And if I want to do a shift, what I'm doing is saying f of x plus, and now I should have probably called it c, but I'll just say c is the constant, okay? So we're adding or we're subtracting outside of the, here's our function, here's our y, right? So notice it's not inside affecting x, it's outside changing y. So for example, we could have the square root of x plus 1, okay? That would shift up. Or we could have the square root of x minus 1, that would shift down. And that's not changing the shape like the last one did. The last one actually changed the shape a little bit, right? It made it bigger or smaller. This takes the graph and either moves it up or down. So like this. And this one, I'm not going to put the actual values for the x because it's going to be pretty much the same. So here's my square root. This is my square root of x. And if I want to say the square root of x minus 1, then what I'm going to do is just take that exact graph. Instead of starting at 0, it's starting at minus 1, and it's taking this exact same path. Okay? Or, so this would be the square root of x minus 1. And the minus 1 is outside of the square root. Or I could say plus 1, and then I'm shifting the entire graph up. I'm trying really hard not to change the shape. So this would be the square root of x plus 1. And we can see that that shift just moves it up or down. So if you have a plus, it goes up. If you have a minus, it goes down. Horizontally, and we're going to do horizontal completely, but horizontally, instead of it being outside the function, it would look more like f of x. And we actually put a minus here, minus c. So you can see the difference. One is still affecting the inside of the function or the x. And here we're outside of the function, affecting just the y, just changing the values of the y there. Okay. So that is our shift up or down. There's only 3 of each, and they're literally the same, but one's vertical, one's horizontal. And then we have a vertical reflection. And that, when we have a vertical reflection, what is happening is it's actually symmetrically flipping over the x-axis. So it flips, and I'll show you, flips over the x-axis. Okay, so for example, if I start with f of x equals the square root of x, then this would be minus f of x, which is equal to minus the square root of x. So if you think about it, if everything for f of x is positive for the square root, now whatever my f of x is, or whatever my g of x is, which would be the negative of f of x, all my y values, excuse me, are going to be negative. So it's literally going to flip down. So if I say, so yeah, I'll do it like this. So I'll say here, g of x is equal to negative the square root of x. So that's outside of the square root or outside of the function. The function is the square root, okay? So when I talk about the function, I'm talking about what those base functions were that we had in 3.3. So if I say that square root of x looks like this, then negative the square root of x, remember, all my values are positive here in the y direction, right? Now, if I say negative, every value here, so let's say this is x comma y. Well, what's going to happen is it's going to come flipped over the x-axis. This is negative the square root, and it's going to be x comma negative y. I should actually do that for all of these. Should I do that? Let me think. I'll do something later. So, but that's really what's happening is all the y values are now negative. And there's really nothing else that's happening. It's only when you have a negative. So if you had -2 times the square root of x, you actually have two different transformations. You have a vertical stretch and you have a vertical reflection, because these values for the stretch and compress, notice I said a is greater than 1. I don't have anything negative here. And here a is between 0 and 1. So the negative happens with this different transformation. And just so I complete it exactly the same way, horizontally, the graph would be f of x, or f of minus x, which is equal to the square root of minus x. Okay, and we'll do that actually now. So these are all our vertical. We have stretch or compress. So this one stretches, this one compresses when it's depending on what A is. These shift up or down, again, depending on what C is. And this just flips over the x-axis whenever it's negative. So now let's talk about horizontally. So horizontally, let's see, I think I'm going to go in a different order because the hardest one is the stretch compress. I think it's the hardest one for people to understand. So I'm going to start with, let's see, I will start with shifts. So shift. Now, if I'm shifting horizontally, it means I'm shifting left or right. Okay, so for example, I think I'll use a different graph this time. I'm going to say f of x is equal to, let's just use x squared. Okay, so if I want to shift, this is where, so horizontally, things are opposite of what they were vertically. Okay, if I say f of x minus c is the shift, then when c is greater than 0, then I'm going to shift to the right. When c is less than 0, I'm going to shift to the left. And that all feels normal until you realize that there's a minus sign in front of the c. So for example, if I say g of x is equal to x minus 2 quantity squared, then this is actually shifting to the right too, because the minus is already there, so c is positive 2. And people get very confused because it looks like a -2, and so people want to move it left. So here's what the graph would look like. So if I start out with my normal x squared graph, should probably stick to an easier one for me to draw. So let's say this is my x squared. Okay. And if I say I want to x minus 2 squared, now notice that's different than when we had it vertically. It was x squared minus 2. Now these are very different. Vertically, it's outside of the function. The function here is squared. For the one we're doing, it's inside the function, so it's affecting the x values. So what I'm going to do is I'm just going to move this graph to the right. And it's not changing shape, even though it may, because it's freehand drawing, but this graph is x minus 2 squared. So most people don't understand why it would do that. So let me just kind of show you. If I plug in, so this point right here, we know is 0, 0, and we want it to go to 2, 0, right? We're not changing the y values. We're changing the x values because we're doing this horizontally. So if I plug in 2 into this graph, into this function, I'll get 2 minus 2, which is 0 squared, which is 0 for my y value, which is what I have here. If I plug in -2, I would get -4 squared, which is 16. So that means when x is -2, it's way up here at 16. Okay, so I know it's confusing, but here we're saying that when that's a negative sign, we're going to shift to the right, and when it's a positive sign, we're going to shift to the left. Okay, so if I wanted to graph h of x is equal to x plus 2 squared, then I go to this point. If I plug in -2 there, I get 0 squared, which is what I'm looking for. And my graph will look like, it's the same parabola. If it's changing shape, it's by accident. So we can see that this would be x plus 2 squared, and it's shifting to the left. Okay, so that's horizontal shifts. Then we can do the reflection. That's pretty easy. And I'll save the best for last. So horizontal reflection, and I will go back to the square root. I think it's the clearest. So we would have f of x is equal to the square root of x. And now I'm going to say, let's make g of x equal to the square root of -x. So notice again, the negative is inside the function, and the function is the square root. So if I were to graph the square root of x, Again, we know it looks something like that. Now, if I want to graph this square root of negative x, well, x can't be positive, because if x is positive, then I have the square root of a negative number. So I can only graph numbers where x is negative, right? Because I still start at 0, but when x is -1, then it becomes +1, and we still get 1, right? So when it's -1, it's still at 1. And we can see that it's going to do exactly the same thing going the other direction. So this reflects over the y-axis. And I find that people find it really confusing when you just say the words, y is horizontal going over the y-axis, but you can see it pictorially because horizontally means it's going this way, right? Vertically would mean it's going this way. So horizontal does reflect over the y-axis and vertical does reflect over the x-axis. And I know it seems confusing until you understand why. So the last one, last but not least, is our horizontal stretch or compress. And I'll say it again, horizontal does opposite of vertical. So horizontal stretch compress it would look something like, let me think of a good graph for this. Oh, I can't really name the function. The best way for me to describe this is not to tell you what the name of the function is, but to show you what it is, okay? So horizontal stretch compress, so it would still be if f of x equals, yeah, I'll just, no. Let me see what I want to say here. I'll just say that we have some function, because I'm just going to draw a function, okay? And if anybody's ever taken trigonometry, then you'll recognize it. It's going to be, I'm going to draw a function that's a sine graph. But we're not doing any trigonometry here. It's just a really good way to explain how it's working. There's very few graphs that I can show you easily. So if I were to draw this graph is going to look like this and like this, and then it's going to continue on forever, okay? And it does the same thing in this direction, okay? So this is the graph that I'm talking about. And I'm just going to say, let's let this be 1, and we'll let this be 2, and we'll do the same thing here, this -1 and -2, okay? So this would be g of x is equal to f of a times x, okay? So now remember the stretch compress vertically was, it's outside of the square root. Here, it's inside the function. It's now affecting x. And what's happening is that if a is greater than 1, it's compressing. And when a is between 0 and 1, it's stretching, which is opposite of what we did vertically, okay? Now, so basically what's happening is it's compressing because it's going, if I say this is f of x, let's just call it f of x, and I want to graph g of x, which I'm going to say is equal to f of 2 times x. So now it's going to compress. which means like if you, I know probably most of you don't even know what I'm talking about, but if you've ever seen an accordion, you probably do. So when you pull it out, I'm calling that stretching. And when you push it in, I'm calling that compressing. So if I want to graph 2 times f of 2x, basically it's going to have within the same, yeah, that's terrible. Hold on. Try one more time. So within the same, I'll just make one. I think that'll be best. So what we did now is notice from here to here, I went up, down, and back. And then I started it again, right? So we're just talking about this part of the graph. So it's going up, down, up, and it's ending in the same place as it did before, right? That is the f of x. This right here is f of 2 times x. So I'll try again. So within that one section here, let me see. I'll do it. I can do it. Yeah, I got it. So within the same space that I originally had just one cycle, now I have 2 cycles, right? So here, 1, and then 2. So I have twice as many cycles in the same amount of space, which means that I've pushed it together. Another way to think about it, I'm not sure what's the best way for you to think about it, so I'll give you a couple of different examples. If this was some particle moving along this axis, then it's going twice as fast now, right? Because let's say this was 2 seconds. In 2 seconds, it only went that far, but when I multiply that x by 2 in 2 seconds, I now go twice as far. I do twice as many cycles. So basically, we compress it. If I want to stretch it, it would look like h of x is equal to f of 1/2 x. Now, within this same, from here to here, I'll only have a half. So here, I think I can do it without too much confusion. It'll just be this part, because now I've stretched it, and then the next 2 seconds, it'll go down and it'll finish out that first cycle. I'll give you some tips on the best way to graph them. Besides, because really right now I'm sketching them, but when you graph them, you have to see like what numbers are doing what. And basically, here, let's do it like this. Let me try this. So I'll do vertical here. And I'll do horizontal here. And I've already graphed them and showed you the basics, but like, let's say I have vertically an x comma y, and horizontally I have an x comma y. Okay, that's what I'm starting with. Now, if I do a stretch or compress, then vertically, I'm gonna multiply the y value by whatever the function, the thing is. So for example, if I have f of x equals a x squared, where a is my stretch or compress, what I'm going to do is my new value is going to affect y. So I would have the same x, but I would have a times y. That's not a of y, that's a times y. So if a is 2, I would have the same x. And let's say, for example, if I had a 0.12 and I have this, and a equals, let's let a equal 2 here, then what is going to change is this is going to become 1, 4, because I'm multiplying the y values by 4, sorry, by 2, by whatever a is, right? Horizontally, if I have, I'm going to still do stretch compress for both of them, then I would say that, and I'm going to use the same values, and I'll even use the same a. What I'm doing here is I'm saying x is changing, y is staying the same because it's horizontal, and x is being divided by whatever a is. So for the point 1, 2, it's going to become 1/2, 2, because all my all my x values are being divided by a because it's compressing. Okay, even if it's stretching, it doesn't matter. So if a is 2, it's going to be 1/2. If a is 1/2, it's going to be 2. So literally the only thing that's changing here is vertically we're multiplying the y value. Here we're multiplying the y value, and here we're dividing the x value. Okay, I said they're opposites. If I have a shift, then if I start with 2, 3, and let's say my shift is, so I'll say f of x is equal to, actually, I'm just going to say we have, I'm going to say we have a f of x plus c. Okay, so if c is greater than 0, then I'm going to add whatever that value is. So let's say c equals, let's just pick a number. So let's say c equals 3, then my new value is going to be, well, I'm vertical, so it's only changing my y value. So it's going to be 2, 6, because I'm going to add 3 to each value, right? Because that's what I said c is. Over here, horizontally, if I start with 2, 3, and horizontally, what I'm going to do is I'm going to have f of x minus c, where c is still 3. So this, what's going to happen here is, again, it's horizontal, so my y value stays the same, but my x value we add 3 because remember c is still positive 3, so we add 3 to this, which makes it 5. Okay, if it was if c was negative, then I'm moving it to the right, I'm sorry, to the left, which means I would subtract 3. Okay, and the shifts, I mean, the reflections are pretty easy. They're just the negatives. So reflections. So vertically, if I'm reflecting a point vertically and I start with, again, any x comma y, it doesn't really matter. I think this one I can leave just x comma y. Vertically, the x's are going to stay the same, but all the y values are going to change to a negative. And the same here horizontally, if I start with xy, then y is going to stay the same because now I'm talking about horizontal, and x is going to be negative. And that's kind of the best way to think about it. All right, so let's start on the slides and we can go really quickly through it. And the pictures will be better. So here again, if C is a positive real number, we're going to go up. And if it's a negative number, we're going to go down. And we talked about this as vertical shifting, okay? So for example, if I have this graph, so what does the absolute value look like? Hopefully everybody knows that it looks like a V, right? It's the absolute value of X. Now, the next thing we have to decide is this a horizontal or a vertical shift? This is vertical because the 2 is outside of the function. The function is absolute value. If it was horizontal, it would look like f of x equals the absolute value of x plus 2. So do you see with horizontal, it's inside the function where I'm saying the function is the absolute value. So that's how I can tell it's vertical, sorry. And so I'm going to add 2, which means I'm going to shift it up 2. So my new graph of the absolute value of x, this is absolute value of x plus 2. And that's really it, okay? So horizontally, again, we said the same thing as this is saying. It's literally, so here it's telling us that the same thing I told you, but let's go over it again. The graph of this is obtained by shifting the graph horizontally because it's inside the function. And remember I said it's opposite. So when you have plus c, it's going to the left. And when you have minus c, it's going to the right, okay? So if we were to graph this, I think I actually graphed this before. So if I start with x squared, and now I have plus c, plus 2. Remember, that means c is minus 2 because I start with basically saying it looks like that. So here c is negative 2, which means it's going to shift to the left 2. And it's inside, this is horizontal. Well, it says so, sorry. So this is horizontal, and you can tell because it's inside the function. So it's literally just going to do something like this, okay? Reflections, again, if it's here, it's outside the function. So this is a vertical reflection. And we're reflecting it around the x-axis because it's vertical. I don't know why it doesn't say vertical, but this is a vertical because it's outside of the function, okay? If it was horizontal, it would be f of minus x. That indicates that it's a horizontal shift or a horizontal reflection. Oh, here's my square root. So we actually already did this. We can see here's the square root of x. It's a lot nicer than mine. And if I again put in minus x, that means it's going to shift over the y-axis, or it's going to reflect around the y-axis and look like that because all my x values now have to be negative to make the graph work. Okay, so now we have a combination of 2 different transformations, right? We have our original function, which we call our parent function. So we can say our parent function, I'm not sure if everybody calls it that, but we'll call it the parent function, which is this, okay? And then we want to sketch this. Now there is an order to this, and the slides I left it'll show you the order, the best order to use, but I think it's easier to think about it like this. Let me show you. So we start off and we have the cube root, and of course that was one that again that you had to really kind of memorize. So the cube root of x, it looks a lot like the square root except it goes in both directions. So this is simply the cubed root of x, nothing else, okay? Now, the order basically goes like this. If I have, like if I were to plug in a number here, let's say I plug in 1, okay, for x. Let's say x equals 1. So I plug in 1 and I get the cube root of 1 is still 1, but that's my base function. I haven't done anything, right? Then the next thing I do is I make it negative. I don't subtract 2 and then make it negative. I say 1 and it becomes -1 minus 2, right? So I actually do, the next thing I do is make it negative, which means I'm flipping, and that's vertical because it's outside of the function, which means I'm going to flip it over the x-axis. So here, let me flip it first and then so now I've flipped it over the x-axis, and this is just the cube root negative the cubed root of x, because all I did is flip it over the x-axis, okay? And then I subtract 2. So next I'm going to subtract 2, because if I were to evaluate it, and I said x equals 1, I would plug in 1, I'd do the cube root of 1 is 1, I'd make it negative, and then I'd subtract 2, right? So the last part of the function is subtract 2, which means it's going to look just like this red graph. We know this is vertical as well. And that red graph is now going to shift down to, and this is where I'm probably not going to do as good a job, but let's just say, I think I left all their graphs in also. So we'll see what, so let's say this was 3, and let's make this 1, which means it's going to start here and it's going to go down like that. And basically, if you see what I did, this is negative the cube root of x minus 2. So the distance between these two graphs, even though it's changing here, is 2, okay, because I've shifted everything down 2. Oh, I know what I did wrong. I made it go through the origin. Okay, I can fix it. Let me fix it. I knew it looked wrong. So it's going to go down to here and like that. Now it looks, that's what it's supposed to look like. So it has the same shape, it's just shifting down. Okay, and let's see, did I leave it? Yes. So again, here it is. This was the original cube root. First thing we do is reflect it about the x-axis, which flips it over, and then we shift it down. And this is the final graph that I had, is the green one, and you can see it kind of matches, okay? And here at 0, it's 0, 0, and here at 0, it's down -2, because it's a vertical transformation. All right, now I don't really like using parabolas for stretching and compressing, because most of the time I hear people say narrow or wide, but narrower or wider is a horizontal term. So taller and shorter is a vertical term, right? Like if you gain weight, you get horizontally wider. You don't get vertically shorter. So I don't like using parabolas. It's hard to tell, but this is a decent picture because so this is this purplish graph is the original x squared. And when I multiply it by 3, if you notice, it's not becoming narrower because it is a vertical transformation. So it's just becoming taller. Basically, this is being multiplied, and that's how I'm getting this taller graph. Okay. And then this is, I think 1/5 x squared, and you can see that it's getting smaller. So it's compressing, it's being pushed down, okay? It's not, don't talk about it as wide, it's short. It's the same exact values, but every value is getting divided by 5. So that's why it's smaller, okay? So if I were to graph 2x squared, well, first let's graph x squared. Now 2x squared, let's do this. So this is 1, 1, right? And there's a point there, and this would be -1, 1. This is just x squared. And let's make a point here. We'll call it 2. And so this would be 4. So 2, 3, 4. And this is -2. So it would be here is, okay. So this would be my just x squared graph. Now, when I go to multiply it by 2, when x is 1, x squared is still 1, but we're multiplying it by 2, so it's here. When it's 4, when x is 2, we plug it in, and we get 4 times 2 is 8. So now that next point is up here at 8, 2, 8. So see, it's all the numbers are being multiplied by 2, so it's getting taller. And this side just is going to match it. Okay. I know everyone says narrower, but narrow is a horizontal term. It's really not the right word. And here is a better graph of what we're talking about. And you can see that x is not changing, but y is doubling. Okay. And then actually, I'm not going to do this one because their graphs are nicer and we've kind of gone through this. So let me just delete this slide completely and we'll just look at what they have. And we can see that so which one is my x squared? Okay, so my x squared graph is the red one. And if I look at 1, 1, let me see what color is good. So if I look at 1, 1, that's the point. I'm sorry. Yeah, that's point x squared, but notice it's at 1/2 here. So right here, it's at 1, instead of being 1, it's 1/2. And at 2, when I plug in 2, I get 4. Half of that is 2. So it's at 2, 2. But the original graph, it's at 2, 4. So that's all that's happening is I'm dividing all my y values by 2 because that's what this 1/2 is doing. Horizontal stretching, compressing. So again, it's going to be different. It's going to be the opposite. So here it's saying if a is greater than 1, if it was vertical, it would stretch. But since it's horizontal, it's compressing. So it's backwards of vertical. And here between 0 and 1, if it was vertical, it compresses, but it is stretching. This is a very bad example. That's why I don't like to use all these examples. To sketch these two graphs. Well, these are two different things. Here, actually, let me do something here. Let me fix this because that really should be inside. This should be, hold on, sorry. So this should be a fraction. Where this is x. Oh, nope. I definitely did not get that in there. Let's see. Oh, I see what I did. Yeah. Huh. Hold on. I'm going to pause the recording for a second while I make it work. Hold on. Okay, I think this will be good. I think we got it. So if I want to graph this function, I start with the square root, and I'm going to have to graph it more to scale. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. I don't think I need to go that high. So I have the original function, which is just square root of x. When x is 1, it's 1. 4, it's 2. 9, it's going to be 3. So here is my square root of x. Okay. And then what I'm going to do here is, this is horizontal. Notice they're both inside of the square root. So I'm basically going to change. So if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, then here, when x is 1, you can see that y is going to be 2, right? But really what's happening is, let me see if I can explain this. I'm compressing it. So this point here has moved this way. It didn't go up. It went to the, it compressed because that 4 is greater than 1. So it's compressing. That point is moving there. And this point at 9, I would have 36. Square root of 36 is 6, right? So at 9, let me do this. So at 9, it would be at 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So at 9, it's actually up here, which is the next point, another point shifted over. Okay, so it's compressing. This is probably a very bad example, but that's what it would look like, because it's the points are moving this way. So this point is actually gone to like here. Okay, and these points are coming from farther out. So it's compressing. If I say 1/4 times x, well, then I have different values, right? So when x is 1, I'm going to have the square root of 1/4, which is 1/2. So it's doing this. But basically, let's do the next one. So when x is 4, it's at 1. And I'll just draw it from there. So this one looks like it's compressing vertically, but it's actually stretching horizontally, because this point, the point that was at 1 is actually now here. Let me get a different color. So this point here is moving that way because it's stretching out. It's like, imagine pulling an accordion, it's pulling that point out, okay? And this point right here is actually somewhere over here. So it's hard to, that's why stretching and compressing horizontally is much more, it feels much more difficult for everybody. But one thing you could do is, what I said was you could divide, remember? So if I have the point, so for example, I think this will help. So if I start with the point 1, 1 here, because for the square root of x, let me write these in, this was the square root of 4x. And this is the square root of 1/4 x. Okay, so if I want to change this 1, 1 for the square root of 4x, basically what I'm doing is I'm dividing the x values, because remember this is horizontal. So this would change to 1/4 1, because when I plug in 1/4 times 4 is 1. Square root of 1 is 1. So notice I'm dividing by the 4. And for this one, if I start with 1, 1, it's going to change to, now I'm dividing by 1/4. So if I say 1 over 1/4, keep, change, flip becomes 4, right? So this becomes 4, 1. Now, if we plug in 4 into this function, I get 4 times 1/4, which is 1. So then I have the square root of 1, which is 1. So you can see that I'm actually dividing here instead of multiplying. It is the harder one, I know it is. Okay, and here's what they're doing. So basically, since their graph is much nicer, let's try it on this graph. This point here is moving, I was moving it the wrong way. So here, let me see if I can get this right. So here, like this, notice here, I'm dividing by 4 because this is 4. So this point here, that's starting here, is shifting to the right. So it's moving this way. This point here is moving this way. So it's compressing all the values. Here, it's stretching them. Okay, hopefully that's clear. So this is the way that they want you to do order of operations. This will work. There's no problem doing it like this where you have to memorize everything. But in general, if you do it in the order of operations, it'll work like this. And you'll see, I'll do an example for you. But if you like this better where they actually point out exactly what's happening, then here it is. So let's look at this. There's a couple of different transformations to do. So let's start out with a graph of, well, we have to start out with a graph of a parabola because the parent function, or the function that it's coming from before the transformation, we can see is squared. So we can say, let's just say y equals x squared, because f of x equals all these transformations. So again, it says do horizontal first, right? But if you do it my way, the way I taught you, the same thing is true. So first, let's just draw out the parabola. So there's just my x squared, okay? And then remember I said, just plug a number in. So let's say x equals 1. So the first thing I do is I add 3, right? Because if I say x equals 1, I add 3 next, and then I square it, right? So because of that, I do the horizontal shift first, which is what they said to do first, but I don't have to memorize because that's how I would do it. So I would do the horizontal shift. So I go left, so I can say I go left 3. Because it's plus, we go left. So 1, 2, 3. And now my new parabola, pretend these are all have the same shape. Okay, I have one that's better that they did. So first I do that, right? And then now that's handled. Then I do 2. So I multiply, actually, let me do it in blue. So now I'm going to multiply every value of y times 2. I'm not doing the negative, that's a different transformation. So it's going to become taller. So for example, maybe it looks like this, okay? And I'm going to erase the original one because I think it's going to get too confusing to have them all here. But we'll do the transformations one by one. And then the next thing I do, so I have 1, I add 3, I square it, I get 16. The next thing I do is I multiply by 2, which gives me my vertical. So the next thing is vertical stretch by 2. Then I make it negative because it was positive 1632. Now it's negative 32. So I have to do my vertical reflection. So so it flips over the x-axis. The x-axis. So I'm going to erase the red one now because the latest one is blue, and now this one is the newest one. So now I'm taking it and I'm reflecting it over the x-axis, and now I've handled all of that part. Okay, because I did my shift, then I did my stretch, then I did my reflection. Okay, now the last thing I have to do is I have to do my vertical shift. So it's -1, so it's down 1. So now that same graph keeps its same shape, it just goes down 1. Okay, so that's when you combine all of them. I don't think you have anything this difficult in your homework, but basically that's how all the different transformations work. And they probably did it in the same order. Well, we didn't have a horizontal stretch or compress. We didn't have a horizontal reflection. So then so basically we did it in the same order, but we did it without the memorizing part. And let me see if I can just copy this and put it here and see if that makes it more clear. So with all our transformations, our final one was this green one. So I can erase the blue one because that was not the final one. And I can erase the red one. That was close. That was everything before I moved it down. And so now I've noticed it's at so the vertex is at -3, -1. And that's where my vertex is, at -3, -1. And that's basically everything. I don't know what else. If you need any help, again, please show up in my office hours. But other than that, I think this is complete, and hopefully you understand everything now. So good luck, and see you at 3.5. Bye.